let's take a look at these answers. Number 22 says a commission is a percentage of a sale. We've had some review exercises that worked with these. It says people who conduct sales earn a portion of their income based on how much they sell. Zachary earned 3.5% commission on a sale of $635. Looks like he's that TV salesman in the picture there. What is the amount of commission? Lana?
$22.23.
Good, just multiply 0.035, 3.5% of commission, times the sale to get $22.23. Good, number 23, Mrs. Cochran bought 1.5 pounds of ground beef. How many ounces did she buy? Lana?
240.
I think you've lost your decimal point.
Oh, 24.
24, there we go, 24 ounces. And a good thing to think is, does this make sense? Well, how many ounces in a pound? Of course, just...
16.
So 1 pound, of course, is 16 ounces. This is 1.5, so it shouldn't be that much more than 16. So yeah, 240, you're like, something's not right. Oh, 240.0, 240 ounces would be correct. And number 24, a word problem, says the sum of 3 consecutive numbers is 42. What are the 3 numbers? Well, Lana, how do I represent any number, first of all?
X.
X. The next consecutive number would have to be,
X plus 1.
and the next number.
X plus 2.
All right, so when it says the sum of these numbers is 42, our equation should be?
3x plus 3 equals 42.
Good. For x, you got what number?
13.
So your 3 consecutive numbers were?
13, 14, and 15.
Good. 13, 14, and 15. What if it had said even numbers, Lana? How would I have represented my first even number?
X.
Well,
No.
x could be anything.
So 2x.
2x would make it even. What would be the next
2.
even number?
2x plus 2.
There we go, because they're spread out 2 apart, and then,
Plus 4.
good. What if it had said any odd number?
X plus 1, X plus 3, X plus 5.
Close. Remember, take any even, add 1, and you're guaranteed odd.
2x plus 1, 2x plus 3, 2x plus 5.
There we go. And those would be our even, or our odd numbers. Had it asked that question, it didn't ask, but wanted to go ahead and review that with you while I had opportunity. All right, I want you to look up further on page 250, right above that. Question number 19 says, what's the difference between a prism and a pyramid? Yesterday, Lana, we were talking about 3-dimensional figures, and I talked about these 2 polyhedrons, or polyhedra, prisms and pyramids, broad categories. What's the biggest difference, in your own words, without looking it up? Let's just see what you remember.
Prism is like tall, and it has like little triangles on the end.
It could have triangles, like the kind of prism you would use in science class would have triangles on the end. Really, though, anything could be on the ends, right?
Yeah.
As long as what's on one end and what's on the other end are exactly the same, congruent to each other, right? So 2 faces would have to be congruent so that there's a uniform shape all the way down or all the way up, right? So there's 2 faces that are congruent, whereas a pyramid always comes to a point. So it only has 1 true base face and comes to a point where the other could have 2 bases, whether they're front, back, or top, bottom. What's required for a 3-dimensional figure to be a polyhedron?
Wait.
Let me ask you this. A 3-dimensional shape could be a lot of things. A sphere, for instance, is 3-dimensional, but it's not a polyhedron. But a pyramid is a polyhedron. What is it that makes something a polyhedron? It's not just the fact that it's solid, but that it's made up of... Flat, there we go, flat faces, good. Made up of flat faces. Where a sphere, a cylinder, do you remember the name of the donut thing?
Torus.
The torus, right?
Torus.
All of those things, right? They're not made up of flat. Like a cylinder has flat, but it's not all flat surfaces, right? So a polyhedron only has flat surfaces. What would we call a polyhedron that has a 6-sided base, but comes to a point at the top? This isn't a memorize, this is a figure it out. If it comes to a point, it's called anything that comes to a point is a pyramid, as long as it has a flat base, is a pyramid. But if it has 6 sides on the base, it would be a Hexagonal pyramid. A hexagonal pyramid.
Hexagonal.
So yeah, just based on, now we did have a special name for a triangular pyramid. It had a special name, a tetrahedron. But otherwise, square pyramid, I think maybe you could make a rectangular pyramid.
Yeah.
You know, you got your pentagonal pyramid, hexagonal pyramid, heptagon, octagonal pyramid, all kinds of stuff like that. All right, dropping down to the bottom of the page now. What are, and we've already mentioned this, the flat surfaces of a polyhedron called?
Faces.
Faces. How many bases do pyramids have?
One.
Only one. What must be true of the, this is almost really, really simple. Imagine you're explaining this to Chloe here. What must be true of the faces of a polyhedron?
They're both the same. Like, wait, what?
What must be true of the faces of a polyhedron? They must be flat. Which, again, it's like, but isn't that what a face is? Well, that's why I said, imagine you're explaining this to Chloe. They gotta be flat. Okay, so a bulgy face wouldn't make it a polyhedron, right? It can't be bulgy at all or sink in at all. It's gotta be perfectly flat. Number 4, what is the name for a single slice formed where a plane intersects a figure? I actually referenced this a moment ago in the Prism. I said you cut it at any point, took a slice. We call that a... You'll look at this in biology next year. You'll get a chance to look at maybe a piece of bone that's been very thinly sliced and put on a microscope slide. We call it a cross-section.
Oh, yeah.
Cross-section of the shape. And again, this is the downside of not having homework last night, is we didn't review any of this last night because we didn't have homework. But we're reviewing now, and that's okay. Number 5. Give a real-life example of each three-dimensional shape. Now, the torus we already said is a donut shape.
Yeah.
Can you think of something else, though, that would be a torus that isn't a donut?
Like a pool floaty or something?
There we go. The inner tube pool floaty thing. I like it. That's what I was thinking as well. All right, what about a rectangular prism? I used this word a lot yesterday. A block would work, okay? A block, a box, okay? A sphere.
Like a bouncy ball?
A bouncy ball, really any ball would work there, right? A cube.
A dice.
Okay, dice, or a die from a set of dice. And then a cylinder.
Maybe like a makeup thing?
I don't know anything about makeup. Maybe think something at Walmart on the grocery aisle.
What's a cylinder?
Anything that's in a can, right? A can of beans, can of peas, can of corn.
I was thinking of something like big.
Yeah, so, well, I mean, they have big cans too, but yeah, cylinder, any of those cans. Even like a tuna fish can, right? It's really short and fat versus like a green bean can, which is a little taller. But it's still a cylinder because it has two flat faces and it's round all the way around. Let's see, for a hexagonal prism, let's picture this now. Okay, so we've got six sides on the front face, right? And let's kind of draw it. And then there's going to be, this is going to be the top. And then this is going to be the side here. And you're going to have this side here. And then inside, you've got, this is kind of a poor drawing, but try to picture this here. How many, first of all, faces would a hexagonal prism have to have?
7? Wait, no. 8.
8. Front, back, and then 6 around, right?
Yeah.
So hexagonal prism would have to have 8 faces. How many edges would it have? I'm going to go out of order here. How many edges would it have? Ooh.
6?
Well,
Wait, no.
there's 6 right here,
Oh.
plus
12. It would have 12.
6 around, plus 6 on the back. Would end up giving you a total of 18 edges. And then how many vertices would it have? So edges would have 18. I went out of order here. And then how many vertices?
It would have 12. Yeah.
12. 6 on the front, 6 on the back. You don't get any vertices on the sides of a prism. Good. All right. Dropping down number 9. Which figure would have 6 rectangular faces? 6 rectangular faces.
Oh, a pentagonal pyramid. Wait, no.
Well, a pentagonal pyramid would have a pentagon and a bunch of
Oh.
triangles.
No.
Which would have 6 rectangular faces.
No.
Don't overthink it.
Yeah, rectangular prism.
Rectangular prism, right? It'd have a front rectangle, back rectangle, top rectangle, bottom rectangle, and 2 side rectangles, right? That'd be a rectangular prism. Which one would have 6 square faces? A cube. Which one would have 1 curved surface and 1 base? A curved surface, a continual curved surface, and then a single base.
Sphere? Wait, no. It's not. Oh, a cone.
A cone. Good. Letter A. Number 12. Which has 1 curved surface and 2 bases?
Cylinder.
A cylinder. Good. Which has 1 curved surface and a hole?
Torus.
A torus. Which one has 1 curved surface and no holes?
That's a sphere.
That's a sphere. Good. Which has 4 faces, all of which are triangles? We sometimes call this a triangular pyramid.
Triangular prism.
Well, no, that would be a prism
no.
as opposed to a pyramid.
Tetrahedron.
The tetrahedron always has 4 faces. Which one has only 1 base? And the 5 other faces, are all triangles.
The pentagonal pyramid.
Good. You have that bottom base, which is a pentagon, and then 5 triangles coming off of it. Good. What would have 2 triangular bases and 3 rectangular faces?
Triangular prism.
The triangular prism. Now, I want to help you visualize something here. If you'll turn back just a page to page 248. I'm not going to go into a lot of depth here, but kind of a neat concept called nets of polyhedra. Nets of a polyhedron. And it's basically taking a solid figure, imagining it to be empty inside, and then folding all the faces out. You look, for instance, at the very top of the page, a triangular or a square pyramid. Well, you would have a square base, and you'd have 4 triangles that if you folded them all up, they would all come together, and that picture you see with a square and triangles all over would be a square pyramid. Well, let's picture a triangular prism for a moment. Triangular prism has a triangle at the front, a triangle at the back, and then the tops are connected, these corners are connected, and these corners are connected. Excuse me, something like that. Let me put it behind more. So we have our triangle, and then coming off of it, we have our triangle here, triangle coming out to the base, and then triangle over here. So we have a base down here on the bottom. We have a back side that's away from us. We have a front side that's toward us. We have a triangle in the back and another triangle in the back, right? Well, imagine for a moment, let me draw this one more time. So triangle here. Something like that. I'm going to go ahead and shade this base in with green. Well, that base is going to be a rectangle. So let's start with a rectangular base, and we'll shade it in with green. Well, right here on this front edge, the triangle would attach to the base, wouldn't it? Imagine if I just flopped that triangle out like that. Well, imagine if I took the back triangle and flopped it backward like that. And then I could take this piece which attaches on this edge, let me shade it in orange. That's this front side here, this rectangular face towards you. If I flopped that over on this edge, I'd get another congruent rectangle. And then if I took the back face, we'll make it blue, which is this one here. If I flopped that over on this edge, I get another congruent rectangle here. And this net, if I went, I could fold it up like a tent. Do you see that? This is a net of polyhedron, a net of a polyhedron. It just takes the figure and folds it out. You see the tetrahedron there. You see that shaded triangular base. Well, that would be that kind of middle-ish triangle you see below it. And you could flop the other pieces out. But what's weird about it is that's not the only way you could do it, right? For instance, what if instead of flopping the orange piece down along this edge, what if instead I took the orange piece and I decided, since it does attach, the orange piece attaches here, what if I decided to flop it out along this edge? I could still do that, couldn't I? So the idea is there's lots of different nets you could take. You would fold this up, this would swing across, and this would come up to meet it. So there's a lot of different nets you can draw. One interesting one you see is the cube there. You see 4 different nets, and those aren't all of them, by the way. 4 different nets of a cube you could make, right? Let's look at the cube just very briefly here. All right, and again, let's use some color coding here. Let's use the pink for my base. Well, of course, that's going to be a square. So let's start by placing our square base. And Lana, if I wanted to take this side right here on this edge, there's only one way really to flop this with relation to the pink. I've got to flop it straight out, correct? So if I take this front piece, it would have to flop out here, correct? But let's suppose that this side here, I can attach it to 2 different things. I could either attach it to this face on this edge, or I could attach it to the base on this edge. Do you want to attach it to the top or to the base?
Top.
Okay, so that means we're going to attach it right on this edge. Well, that's this edge, correct? So that means it would flop out here, wouldn't it? But you see what's attached back here is this back, use yellow now, this back face is attached to this side face we just flopped right here, isn't it? Right? Now that's right there. And if I were to, let's see, flop this down, no, excuse me, if I were to swing this out, right, this is the green edge, the yellow edge is parallel, this is the yellow edge. So I could then swing that out off of that one, couldn't I? If I were to take the back side here away from us, that I could just maybe flop off the base again on this edge, which would be here. And then the top attaches up here on this edge. So down here, flop it out, and then on the other end is where the top would be. Let's just make the top, I haven't used orange yet. And then the top could fold out right here. And I don't think, the book does have that one. Never mind, I see it now. They just turn it up and down. But there's all different ways to make nets of polyhedra. It's just an unfolding idea. Now, the good news for you is I'm not really going to test you on that kind of thing. It would be good for your analytical skills to see it, but you're not really going to be tested. Let's do a couple quick drills just to see if we can kind of piece this together here. Look at, say, number 16 across the way. Drop down to number 16. If we were to fold all those pieces up, what shape do you think we would get?
Rectangular prism.
A rectangular prism, good. What about number 17? Now it's got circles, so it's not a fold, it's a fold and curl kind of idea. What do you think we get for 17?
Cylinder?
A cylinder, good. You have to fold the circles up and then curl around the circles to finish it. What about number 18?
A cube. Wait, no, that's not.
You have to fold that first triangle that attaches to the square, and then all the other triangles will just keep folding around the square. Be
The pentagonal pyramid?
a square pyramid.
Or
A square pyramid. That first pyramid here, that first triangle would fold up, then the next triangle, as it folds over, would attach to the base. Then when you fold the next one over, it would attach to the base. So you fold the next one over, it would attach to the base. So you'd have a square pyramid from that. If we were to turn over to page 251, number 7 at the top of the page. What shape do you think we'd get from that net, that orange net?
Pentagonal prism?
Good, a pentagonal prism, fantastic. Number 8 is a choice, A or B. Which one would form a rectangular prism? This one's going to take a little bit of thinking.
B?
Well, you know what shape the cross section is because you see the little short rectangles?
Mm-hmm.
So you know it's going to be really short and it's going to be wide. Well, here's the deal. If you have short, wide, that means you've got to have 2 pieces that are short to go on the ends, and then 2 pieces that are wide to go on the top and bottom, right? Can the 2 wide pieces be right next to each other?
No.
No, they've got to have 2 short pieces to come between the 2 wides. So it's got to be letter A for that reason.
Yeah.
Do you see how you got 2 wide pieces right next to each other on B? So again, it's just a little bit of thinking. Now, the real idea behind these nets, though, is it allows you to kind of visualize a concept called surface area. For instance, if you were to take a rectangular prism, Lana, you could fold that thing out into something like this, and you could figure out what the area would be. Is that yours?
Yep.
Okay, for a minute I thought Glenn dropped it and somehow made it all the way up there. I'm like, how did he do that? Okay, no. All right. Just the weird way my eyes saw it. I was like, did that come all the way from over there? All right. But you can fold out a figure, and that'll help you figure out, well, I already know area formulas for flat things, so in 3 dimensions, what would we get? Turn over to page 254 now. Page 254. You see in yellow there, you see a bright yellow, a deep gold, and a light yellow on your rectangular prism. You see that the ends are that goldy color. The brighter yellow is the front and therefore the back as well. And then the light yellow is the top and the bottom. When you fold it all out, there's your various shapes. As you look at this, there's 2 types of surface area we want to talk about. The first type of surface area literally measures the area of every single face or every surface of the prism or of the pyramid or even of the 3-dimensional figure. And so for a rectangular prism, what we've got here are we've got 2 rectangles that have a length and height. We have 2 rectangles that have a length and width, and we've got 2 rectangles that have a width and height. And you can see those double rectangles listed out there. That gives us a formula for the surface area: 2 length times width, 2 length times height, 2 width times height. Does the order of these necessarily matter? No, addition's commutative, as long as you have length and width together once, length and height together once, and then width and height together once. And you see how unfolding into a net can help you to visualize that surface area. But there's another concept besides surface area. It's what we call lateral surface area. Lateral surface area. Lateral always refers to that which is sideways, or that which is on the sides. Well, if we were to picture this room, Lana, we see that there are 4 walls, 2 front walls, back wall, 2 side walls, right and left, and then there's a ceiling and there's a floor. We're in a great big box. That's a weird way to think of this room. But if we were going to paint the room, well, you don't paint the floor, you put carpet on it. Most people don't paint ceilings unless, they're stripping the popcorn ceilings off and then painting them in white. But you would typically paint your walls. Well, if you ignore the top and bottom of the figure and you just look at the enclosing sides, we have what's called the lateral area. So we don't necessarily care about the length and width of the room. We care about the length and height, which would be the side walls, and the width and height, which would be the front and back walls. So if you just take this out, we have what's called the lateral surface area. We'll use LA for lateral area. It basically just omits the 1 and does 2LH plus 2WH. And you see that formula there as well for lateral surface area. What's the problem? Okay, I don't know if your hand was up. All right, so questions on lateral area. I believe you learned about this last year, am I correct?
Yeah.
Okay, so this is a review concept for you. Now, you understand a cube is a rectangular prism. So for a cube, it's going to be very similar, except length, width, height, they're all the same, right? So we could just put, for a cube, we could put just the length of one edge, couldn't we? Well, 2 edge edge is 2 edge squared. 2 edge edge is 2 edge squared. 2 edge edge is 2 edge squared. 2 edge squared plus 2 edge squared plus 2 edge squared is 6 edge squared. And so for a cube, 6e squared will give us the formula for the surface area. If all you wanted was the lateral area, you cut this out, well, that'd be 2 edge squared, lateral area, 4e squared. And here are our formulas for the rectangular prism, surface area, lateral area, and cube. Again, the bigger picture, though, is rather than just memorizing the formula, kind of picturing it as well. One more figure that we want to kind of throw into this category of memorized things would be that square pyramid. The square pyramid. Now, the square pyramid is kind of interesting because a pyramid, you understand, does have an actual, okay, let's see if I can draw this. A pyramid does have an actual true height, right? Like if you were measuring from the ground to the top, but that's hard to measure without getting inside the pyramid, right? Or without using some sort of measurements. If you were to measure from the ground and you were to go up, up, up at a slant, you wouldn't get the real height of the pyramid. You get what we call the slant height. That's what we're going to use here. If you look on the next page, you see that picture of the pyramid. And we're using h, but it's not really the height, but the height of the triangle itself when you fold it out. You see the net there of the square pyramid. So for the surface area of a square pyramid, first of all, you have a particular length of the base. Well, since the base itself is a square, length of base times length of base would be base squared. And then there are 4 individual triangles. You would add the 4 triangles onto that, and each one, of course, is a half base times, again, this slant height, where it's perpendicular to this base. So since each one's a triangle, half base times height. Well, if you were to multiply 4 times a half BH, the 4 and 2 could cancel to give us 2. So we could say, if we're lazy and we don't want to have to do all that extra work, 2BH, where we just need to remember that the H here isn't actually the height of the pyramid, but the height of the triangle as you go up at the slant. We call it the slant height. Questions on that? But if you were to paint a pyramid for some odd reason, we're like, you know what, the pyramids in Egypt, that brown look is so out. And Lana's like, they would be so much prettier if they were pink. And so Lana goes there with her spray paint. She spray paints the pyramids pink. How much spray paint we gonna need? Well, you don't have to paint the base, right? You would only have to paint the 4 triangular faces. So the lateral surface area just omits the b squared and would be 2BH, where again, the h would be the slant height. Now again, you can memorize these, or you can just be like, well, duh, based on the way the net folds out, it's gotta be this. Probably the best plan would be to go ahead and memorize them. But let's face it, our memories sometimes slip up. So if you can think it through, even on a quiz, like, oh, I don't remember how to do this. Well, let me figure out how to do it. And that may work as well. Look at example 6.4a very quickly. They give you that blue box, that blue rectangular prism. They ask for the surface area and the lateral surface area. Notice the dimensions 18 by 5 by 10. Well, they plug into the surface area formula. 2LW, 2WH, 2LH. Multiply it all out. They double the 18 times 5. They double the 5 times 10. They double the 18 times 10. Add all of those together to get 640 square inches of surface area. Then they asked for the lateral surface area. Well, forget the 2LW, so forget the 218 times 5. Just go with the other two, and that adds up to 460. Do you see how to use the formula? Again, you did this last year, so it shouldn't be too bad. For letter B, they have the cube, where one edge is 4 meters. Well, again, each face is edge squared, and there are 6 of them, so 6e squared. Square the 4, multiply by 6, 96 square meters of surface area all the way around. But if you only wanted the 4 walls, if you will, 4e squared, which is 64 meters squared. Questions on that? Look at the next page. Example 6.4b. They give us a very flat, short square pyramid. Well, they use the formula 4 times a half BH plus the b squared. Well, the base is 14. I would start by squaring the base, either one of these, to get the 196, but also the half BH. Well, half of 14 is 7 times that slant height is 63, but there's 4 total of those 63s to get a total of 252 square inches, plus the 196 gives you the 448 square inches. Questions on that? All right, turn over to page 256. Page 256. I want you to do numbers 1, 2, 3, and 5. Page 256, numbers 1, 2, 3, and 5. Using these formulas, find the surface area and the lateral surface area for each of these. Skip 5 on lateral area. You don't need to do lateral surface area on 5, but do the surface area and lateral surface area of the others. Yeah, I would say the width is 5, the length is 9, and the height is 2. The height is definitely 2. Again, you can call the 5 the length and 9 the width or the depth. Doesn't really matter. As long as you call the height 2 is the main thing. On number 1. The nice thing about using lateral area is you've already multiplied these two, so you don't have to multiply them again. You already know what they are. You just have to add just those two. Or you can subtract this away once you've found your first answer. So instead of doing the whole process again, use some of the things you already did to your advantage.
So you add the...
So, for instance, Lonnie, you said the 2 times length times width was 2 times 5 times 9, right? Mm-hmm. And then 2 times 9 times 2 for 2LH?
I put 2 times 5 times 2.
Okay, that's fine, because here you would have done 2 times 9 times 2, right?
Yeah.
Yeah, so it really doesn't matter, same things either way. So here that added up to 90, here to 20, and here to 36, right? What did you get for your surface area?
146.
146
Square inches.
square inches. Okay, I couldn't remember what the unit was. Well, we're not going to redo any of this. We're just going to say, well, all I really need are these two. And instead of doing any more multiplication, I just write down.
Oh, you just add 20 plus 36. And then
Is.
56.
And boom, we're done. So the neat thing about finding lateral area, if you already found surface area, lateral area means, okay, just ignore the 2LW that you had, whatever that was, in this case 90, and just add the rest of it for your lateral area. So you can save yourself time. You don't have to actually plug in all the numbers again and do all that extra work, because mathematicians are lazy. Good. So Lana, for the cube, you found its surface area given an edge of 12 to be what?
Wait, you want
Yeah, the answer.
865.
Good, because you did 6 times
12.
times 144, right?
Yeah.
All right, so this time you're not going to do 6 times 144, you're going to do,
4 times.
there we go, and that'll give us, just multiplying it out,
576.
576 meters squared. Again, instead of multiplied by the 6, multiply by the 4. Now granted, 12 squared isn't hard, we do that in our head, right? But if it were something like 76 squared, I mean, mercy, well, once you squared it here, for heaven's sakes, don't re-multiply 76 times itself. You already know what it is. Here, we already know it's 144, copying it down. Good. Looking at the next one with the square pyramid. Again, I would use the edited formula. It's not in your textbook. This is my personal formula for square pyramids surface area, because it avoids fractions, and I hate fractions. So b squared plus 2bh, where again h is that slant height. That's what they give you. They don't give you the true height. They give you a slant height.
Five.
105. But, Lana, what was the unit again? Meters squared.
Meters squared.
But I'm not going to reinvent the wheel here. I already did the 2bh. So I already know what the lateral surface area is.
56.
56 meters squared.
Oh.
And so even though it's another step to write out an answer, it usually doesn't involve too much more math. Do you see that?
Yeah.
So it's not that much harder to do the lateral area. Drop down and do number 5 now, just the surface area. Just the surface area. We'll scrap the lateral surface area on 5. All right, what you got?
245.76 inches squared.
Great job, 245.76 inches squared. I want you to look at number 4 with me. And I'm going to go just a nudge past the bell, so stay with me here. But on number 4, that tent-looking thing, it has one face on the front, one face on the back. Those two faces are both,
4. Wait.
well, what shape are they? The two faces on the front and back
Triangles.
are triangles. And it has how many other faces, Lana?
2. I mean 3.
3. A bottom and 2 sides. It's kind of like a tent, isn't it? There's 2 sides and a bottom to it. So there are 3. Now each of those faces is what shape?
Rectangle.
Rectangle. So there are 3 rectangles and there are 2 triangles. But for it to work, to be a prism, Lana, we know that 2 triangles have to be congruent. And the 3 rectangles all have to be congruent also, don't they? So for the rectangle, look at the picture with me. What are the dimensions of the rectangle? Each rectangle is how long
14 centimeters.
and how tall on a slant.
4 centimeters.
Careful, that's the height to the peak. The slant is actually
5.
the 5. So each rectangle is 14 by 5. So go and do that on at your seat real quick. 14 times 5 is 70 centimeters squared, right? But there are 3 of these rectangles.
Then it would be 210.
210 centimeters squared. Now each triangle, remember, its formula for a triangle is a half base times height, right? What is the width of the base of each triangle?
6 centimeters.
6. And the height of each triangle is
4.
the 4. But we want half of that. So what is the area of each triangle?
12.
12. But there's 2 of them to give us.
24.
So what's the surface area of the tent?
234 centimeters.
Excellent. So even weird shapes that don't have formulas, you can kind of figure out what they must be. You're going to be trying one of these in your homework tonight. If you look across the page, notice number 2. You're going to be trying one of those tent-looking things. So I want to take a look at one of those with you. For homework this evening, page 257, numbers 1 through 9. Page 257, numbers 1 through 9. And back on page 251, numbers 18 through 24. Back on page 251, numbers 18 through 24. So again, page 257, 1 through 9, the homework section, and page 251 in the homework section, 18 through 24. All right, you are dismissed. Have a wonderful rest of your day.